Hello, grade 10s. In today's lesson, we are going to complete the discussion on the atom. In the last lesson, we learnt about the different energy levels and the different shells. And it's very important that we can conceptualize it, that we have a mental image in our head of how an atom is arranged. But what we're going to learn now is how you will show electron configuration on a test or on an exam. So the arrangement of electrons around the nucleus of an atom, that's called the electron configuration of an atom. And when we provide the electron configuration of an atom, it automatically applies to an atom in its ground state, not in its excited state. So it hasn't gained energy and moved up energy levels. It is in its normal ground state. We're only going to consider the electron configurations of elements 1 to 20. So we're only going to go from hydrogen to calcium. We are not going to consider the electron configuration of elements 21 onwards. To represent the electron configuration of an element in its ground state, one way of doing it is by representing an Aufbau diagram. Using the Aufbau principle, we can draw an Aufbau diagram, and in German, Aufbau means building up. The principle states that electrons occupy the orbitals of an atom in orders of increasing energy. Now remember that n equals 1 has less energy than n equals 2. N equals 3 has more energy than n equals 2. So we're always going to first occupy n equals 1 before we move on to n equals 2, n equals 3, etc. We need to know the energy order of the orbitals, and then we can show how the electrons fill up these orbitals. So we're going to start off with a generic setup of an Aufbau diagram. So whenever you're asked to draw an Aufbau diagram, you have to set it up like this. You need to show an arrow up, and you have to state energy next to that arrow. That shows an increasing energy. Now, in the first energy level, we have a 1s shell. In the second energy level, we have a 2s shell and then a 2p shell. The p shell has more energy than the s shell, so we go from 1s to 2s to 2p. Then we move on to the third energy level, which has an s shell and a p shell. And remember that we end off at the fourth energy level and at the S shell of the fourth energy level. Note that we're going to draw a block that aligns with each S shell. They have to align with each other. And the P shell, remember, consists of 3 p orbitals. So we have to draw 3 blocks for every P shell, and they have to be orientated with each other. So you're going to have to remember how to set up an Aufbau diagram. We also need to keep in mind 2 very important things: Pauli's exclusion principle and Hund's rule. Pauli's exclusion principle tells us that an orbital can only hold a maximum of 2 electrons, and those 2 electrons have opposite spins. Remember that electrons, they don't like each other because they're both negatively charged. So in order to minimize repulsion, they have opposite spin so that they don't have to come across each other. Hund's rule tells us again that because electrons want to minimize repulsion, they're going to fill the orbitals of a shell with their spins in the same direction before pairing. This is a little bit difficult to explain without a diagram, so I will bring you back to Hund's rule as well as Pauli's exclusion principle in a moment with diagrams. Let's take a look. So the Aufbau diagram of hydrogen looks like this. Remember, this is our normal Aufbau diagram setup. Hydrogen has 1 electron. I chose an up arrow. We can start with a down arrow, it doesn't matter. But if we're going to start with a down facing arrow, then we've got to keep it consistent. If we start with an up facing arrow, again, we got to keep it consistent. Here's the Aufbau diagram of helium. So helium has got 2 electrons in the first energy level, 1 up and 1 down. And that follows Pauli's exclusion principle. So the 2 electrons within this orbital have to have opposite spin according to Pauli's exclusion principle. This is an Aufbau diagram of a lithium atom. So we've got the 1s shell that's been full, and then the 3rd electron of lithium is going to join the s shell of the 2nd energy level. Next comes beryllium, which has 4 electrons. Again, we are assuming with all of these atoms that they are neutral. So the first 2 electrons are going to fill up the first energy level, n equals 1, and the next 2 electrons are going to fill up the s shell of the 2nd energy level. Next comes boron. So boron's first 2 electrons are going to fill up n equals 1. The next 2 electrons are going to fill up the s shell of n equals 2. The 5th electron, because boron has 5 electrons, will now move on to the p shell of the 2nd energy level. Now, carbon is where we can see Hund's rule in action, because the first energy level is going to be filled up as far as the s shell is concerned. There's only an s shell. The 2nd energy level is going to be filled up at the s shell. Now that the s shell in the 2nd energy level has been used up, the next electron goes into the p shell, but the one after doesn't go into the same orbital. It goes into the next p orbital in the same direction. So both of them are up-facing arrows. And again, they're going to do that before pairing in order to minimize repulsion. For nitrogen, the 3 p shell orbitals will each have 1 electron with the same spin. So now, the next atom, which is oxygen, which has 8 electrons, so we've got 2, 4, 5, 6, 7 facing up, and the 8th one is now going to pair up with the first electron that had filled up the p shell in the 2nd energy level, and so on. We may also represent the electron configuration of an atom using SP or spectroscopic notation. So electron configuration can be shown with either Aufbau diagrams or with SP notation. Now, hydrogen has 1 electron in n equals 1, which is the first energy level, and the first energy level only has an s shell. So its SP notation or spectroscopic notation is 1s1. This one represents the first energy level, this S represents the S shell, and this 1 represents the 1 electron that lives within the S shell of hydrogen. Helium has 2 electrons in n equals 1, again within the S shell. It fills up the S shell. So its spectroscopic notation is 1s2. What we need to note is that helium's outermost energy level, which is n equals 1, is full. So the first energy level can hold a maximum of 2 electrons, and helium, which is a noble gas, has a full outer energy level, meaning that its N equals 1 is full with 2 electrons. And that is what defines it as a noble gas. We will understand in the next section why elements that have a full outer energy level, they don't like to react with anyone. They have no need to chemically react and form bonds. And that's what makes them noble gases. Now, lithium has 2 electrons that are going to fill up the first energy level, obviously the S shell of the first energy level. Lithium's third electron is going into the S shell of N equals 2. So the SP notation of lithium is 1s2, 2s1. 1s2 indicates to us that the first energy level, N equals 1, is full. And the third electron is going to go into the S shell of the second energy level. If we add up these superscripted numbers, 2 plus 1, that adds up to 3. And that is the number of protons in lithium, which is equal to the number of electrons in a lithium atom, provided that the lithium atom is neutral. Beryllium is going to have the first 2 electrons filling up the first energy level. The third and fourth electrons are going to fill up the S shell of the second energy level. So the SP notation would be 1s2, 2s2. Boron has 2 electrons in the first energy level. Its third and 4 electrons are also going to sit over here in the 2s shell, but it has a 5th electron that now has to fit inside the p shell of the second energy level. So the spectroscopic notation of boron is 1s2, 2s2, and 2p1. Again, if we say 2 plus 2 plus 1, we get a number of 5, which is the number of electrons that are present in a neutral boron atom. Carbon's electron configuration, well, its 1s shell is full, its 2s shell is full, and in the second energy level, it has 2 electrons in the p shell. Nitrogen has a total of 7 electrons, so it's going to be 1s2, 2s2, and 2p3. Note that we're not differentiating between the different p orientations here. A p shell can hold up to 6 electrons in total because it's got 3 p orbitals. So we do not differentiate between the different p orientations. We just go 2p1, 2p2, 2p3. The highest that it can be is 2p6 because a p shell can hold a maximum of 6 electrons. Oxygen's electron configuration is 1s2, 2s2, 2p4. So 4 plus 2 plus 2 is 8, which is equal to the number of electrons in a neutral oxygen atom. Electrons that are in completely filled energy levels are called core electrons. Now, in the case of oxygen, what is a completely filled energy level? Only the first energy level is completely full. The second energy level is not completely full. The S shell is, but the second energy level as a whole is not. When we look at core electrons, we're looking at electrons in completely filled energy levels. So, again, in the case of oxygen, the only core electrons it has are the 2 electrons in the S shell of the first energy level. And what are core electrons? Core electrons are electrons that are unreactive. And that means that they do not get involved in chemical bonding. They are not directly involved in chemical reactions. But electrons in the outermost energy levels are called valence electrons. Valence electrons are the number of electrons in the outermost energy level, and those electrons might be gained, they might be lost, or they might be shared in order to create bonds with other atoms. And we're going to learn more about the types of bonds that can exist. So in the case of oxygen, we have 2 core electrons. How many valence electrons do we have? We've got 4 plus 2. We've got 6 valence electrons. The second energy level of oxygen holds 6 electrons of a possible total of 8 electrons that can be held by the second energy level. If you didn't understand the explanation on the number of valence electrons in oxygen, don't worry about it. In the next section on the periodic table, it will become very, very clear with lots of diagrams how many valence electrons each atom holds. So it will make a lot more sense later. Now, why are noble gases unreactive? The simple answer is that noble gases have an outermost energy level that is full, meaning that their n equals 1 is full, or their n equals 2 is full, or their n equals 3 is full. All atoms tend towards their lowest energy state, and that applies to all natural systems. We kind of all tend towards laziness. A ball will roll down a hill to a lower state of potential energy. That's just how natural systems work. In the same way, atoms also tend towards a state of lower energy. Now, atoms that have valence electrons, meaning that they have a certain number of electrons in their outermost energy level, but it doesn't fill up their energy level. They could actually reduce the energy state through bonding. So that is why many, many atoms will create chemical bonds, but noble gases will not create chemical bonds. Note that there is a difference between valence electrons and valency. Valence electrons refers to the number of electrons in the outermost energy level of an atom, and valency is the number of electrons that an atom needs to gain or lose in order to have a full outermost energy level. Now, these are very important definitions and very important concepts that we're going to take forward with us when we learn about chemical bonding. But in the meantime, we need to know these definitions, and it will certainly make more sense once we have discussed the next section on the periodic table in more detail. For now, let's end off this lesson with a short exercise. I'd like you to pause the video and try these questions on your own, and then play the video to see how much of this you've grasped. Provide the SP notation and Aufbau diagram of the following elements: fluorine, sodium, chlorine, and calcium. Fluorine has a total of 9 electrons when it is neutral. So the electron configuration in terms of the SP notation is 1s2, 2s2, 2p5. 5 plus 2 plus 2 adds up to 9. When we draw the Aufbau diagram, we've got to show those 9 electrons using arrows. We first fill up the 1s shell, we then fill up the 2s shell with arrows that have opposite spins. Then we go on to the 2p shell. We use the up arrow, up arrow, up arrow before we come back to the last 2 electrons, 8 and 9, that then pair up with the original p's, but in opposite spin. Sodium. Sodium has got a total of 11 electrons. 1s2, 2s2, 2p6, 3s1. So sodium's first energy level and second energy level are full. Its core electrons are in n equals 1 and n equals 2. And it has 1 valence electron in the third energy level. And of course, you'll also notice that sodium is in period 3. When it comes to the Aufbau diagram, we fill up the 1s, we fill up the 2s, we fill up the 2p, and the last electron, the outermost electron of sodium, is in the s shell of the third energy level. Let's take a look at chlorine. Chlorine has a total of 17 electrons in a neutral atom. So the first energy level is full, 1s2. The second energy level is also full, 2s2, 2p6. There we go. The third energy level is not full. The s shell of the third energy level is full, and the p shell holds 5 out of the total of 6 electrons that it could potentially hold. So 2, 4, 6, 8, 10, 12, 13, 14, 15, and then opposite spins down, 17, 18. And calcium. Calcium is element number 20. Calcium is going to be the most complex atom for which you will need to provide the Aufbau diagram and the SP notation, because we end off on element number 20. That's calcium. Now, in the case of calcium, calcium exists in the fourth period of the periodic table, meaning that its outermost electrons are in the fourth energy level. So the first energy level, 1s2, is full. The second energy level, 1s2, 2p6, is full. The third energy level is also full, 3s2, 3p6. The fourth energy level is very partially filled. Only the s shell of the fourth energy level is full. So only 2 of the 18 electrons, potential 18 electrons, exist in the fourth energy level of calcium. The next question asks us how many core electrons and how many valence electrons are found in each of the following elements, and in which energy levels are they found? I'm going to go back to the first question. It's very difficult to discuss it without a visual. Fluorine has got 2 core electrons in n equals 1. Is its n equals 2 full? No, it's not. So we have to count the number of electrons in the unfilled outermost energy level, and that will tell us the number of valence electrons. So fluorine has 2 core electrons in n equals 1, and it's got 2, 4, 6, 7 electrons. Those are valence electrons in n equals 2. Sodium, well, we can see that its first energy level is full and its second energy level is full. So sodium has 2 core electrons in n equals 1. It has 8 core electrons in n equals 2, and then it's got 1 valence electron in n equals 3. Chlorine, well, we can see that the first energy level is full. We can see that the second energy level is full. So we've got 2 core electrons in n equals 1, 8 core electrons in n equals 2, and n equals 3 is not full. Therefore, these electrons are valence electrons. 2, 4, 6, 7 valence electrons in n equals 3. In the case of calcium, we have 2 core electrons in n equals 1, 8 core electrons in n equals 2, 8 core electrons in n equals 3, and the fourth energy level contains 2 electrons. That's not a filled energy level. Therefore, calcium contains 2 valence electrons in n equals 4. Here are the answers. Let's now just consider helium and neon. They're both noble gases. In the case of helium, the first energy level is full. But even though the first energy level is full, valence electrons are defined as the number of electrons in the outermost energy level of an atom. So helium's first energy level, and only energy level, contains 2 valence electrons, which fills up the first energy level. So we consider it a full valence energy level. In the case of neon, well, the first energy level is full, so it definitely has those 2 core electrons in n equals 1. Now, its second energy level is also full. It contains all 8 electrons that the second energy level may contain. And again, we consider it valence electrons rather than core electrons, but we consider it a full valence energy level. So there's just a bit of a difference in the definition of valence versus core when it comes to noble gases. So noble gases do have core electrons in any filled energy levels, but even though their outermost energy level is full, we still consider those valence electrons, not core electrons, but specifically we consider it a full valence energy level. If any of this didn't make sense, in the next section on the periodic table, there are lots of diagrams and lots of visuals. So it will definitely all come together in the next section.